Okay, questions on stuff with the class right now? All right. So, so let's go on. What we're going to do is I want to remind us where we were. All right. Let's actually, before we even look at this, let's just remind ourselves where we were at the end of, right before everybody went home for break. Um, so we were doing shapes of molecules is what we had built up to, right? How do you determine the shape of a molecule? All right, and so let's say I had something like H2S. So this is the smell of rotten eggs. It's also the smell if you, I think it's the smell that you get from when you, very slightly when you turn on the gas for your gas stove and it isn't lit yet to let you, and it's because the natural gas that's in there doesn't smell like anything and they want you to know that the stove's on so you don't blow up your house essentially. Um, so if we want to do this, if we want to figure out the shape of that, first you need to do a Lewis dot structure. All right, and then you determine shape. And you're going to determine the shape based on the number of electron groups around the center atom. I should be typing this because that's probably barely legible. But so let's go ahead. In terms of Lewis dot structure, I'm just going to run through it quick because we got lots of stuff we're going to talk about today. The first thing I do is figure out how many valence electrons I have to play with, right? So number of valence electrons, 1 for hydrogen, it's on the left-hand side there, 1, and then 6 for sulfur. I'm sure you guys remember this, but remember for things like, for hydrogen, 1, because I'm counting from the left, from sulfur, 1, 2, 3, 4, 5, 6. We've talked about how the theory or how that comes from electron configurations. And really, electron configurations are driving the structure of the periodic table. All right, things on the periodic table are grouped according to their reactivity. So these all react the same, these all react the same, not the same, but similar. These all react in similar ways, etc. But the reason why they react the same is they have the same number of valence electrons, and that's what we get out of our electron configurations. So that's one of the models we're working with today, or right now in the class. We will have more models. So the total number, and our Lewis dot structures can be more complicated than this, but we have the total number of electrons we get here are 8. So I'm going to put my sulfur in the middle. I'm going to attach it with single bonds to hydrogens. I'm going to make sure everybody has a full octet, starting with the outside atoms, except hydrogen. What's up with hydrogen? It only gets 2, right? Because if you look at that top row of the periodic table, you only have 2 things there. It only has an S orbital or an S subshell. So that's good, that's good. I need to fill up the sulfur. I have 2, 4 electrons, right? 2 for each bond on the sulfur right now. So 2 there, 2 there. And so I have 4 more to add to get it to 8. And I actually have 4 more. That was lovely. All right, so we'll do that. All right, and that's my Lewis dot structure. Now I need to determine the shape. And for this, you can think about what shapes you would get if you spread these 4 electron groups. So I have a bond, right? If this was a double bond, it would still be 1 electron group. If it was a triple bond, it would still be 1 electron group. Okay, we haven't encountered quadruple bonds in here. But I have a lone pair. This is an electron group. So 1, 2, 3, 4. What's my electronic geometry for? And so you either have this memorized from, it's not going to come up on a test again, except the final, right? It's not going to come up on test 3, but electronic geometry, so you have to have this memorized or just kind of know the shapes in your head. What's the electronic geometry here? In other words, in space, all the electron groups, what shape do they make? Tetrahedral. Great. Okay, and then we have a molecular geometry. What's different about the molecular geometry? Don't tell me the shape. How is it different from the electronic geometry? It only counts the atoms, the shape of the atoms, okay? So we have two groups attached to a sulfur, all right? So it can't be a tetrahedral because that'd be four atoms attached to a sulfur for molecular geometry. But what's the shape going to be? So I've got two electrons here. I've drawn it. It looks linear, but it's not linear. What is it? It's bent. Okay, so if my legs here, I can see I might fall down today during my lecture, but my legs are my hydrogens here. A tetrahedron looks kind of like this. All right, so I'll turn like this, I guess. Okay, but if my hands are the lone pairs, that's a tetrahedron, and so I have a bent shape. This is exaggerated for what it is, but I have a bent shape for that molecule, so it's going to be bent. Questions? Okay, then that leads right into our next concept where we're going to talk about polarity. All right, so far we've talked about covalent bonds, right? We talk about a covalent bond. This is a bond where what happens? How do we make a covalent bond? You guys are as dead as I feel. I'm really looking forward to coffee in about 2 hours. Each atom donates an electron, right? And they're shared, okay? And atoms do this to fill out their octet. All right, what we've talked about though is they're shared, and I've kind of given you the impression that they're shared equally, or just haven't talked about how they're shared. Well, they can be shared equally or unequally, all right? So the electrons in a covalent bond can be shared equally or unequally. All right? When electrons are shared sufficiently unequally, and we'll talk about what sufficiently is, okay? So when they're shared sufficiently unequally, we get what we call a polar bond. And more specifically, a polar covalent bond. All right? And so how do we know whether they're shared equally or unequally? We have a concept that's related to electrons and atoms and how much an atom wants electrons. What's that concept? Do you remember electronegativity is how much an atom wants electrons? I'll put wants because I'm anthropomorphizing it. Okay, it's kind of a mix of our electron affinity and our ionization energy. All right, and so if we have something like hydrogen, and let's say we have a bond between hydrogen and oxygen, okay, this isn't a full structure. We'll just look at the bond here, but which of those atoms, look at the periodic table, remember your electronegativity while I tie my shoe, which of those atoms wants electrons more? What was it? The oxygen wants electrons more, all right? And so the way we would draw that is we like to draw these little arrows that point to where the electrons are going. And then we put a little plus sign over here to show the plus side, okay? So what we have here is we have a plus side and a minus side. And so what would happen here is we wouldn't end up with these full charges we talked about previously, right? For ionic compounds, we've talked about you +1, +2, -1, -2, etc. Okay? We'd end up with what we say, we use this as a calculus term. It's a baby delta, means partial. We have a partial positive charge on the hydrogen. We're not going to do any calculus in here. And a partial negative charge, okay? So partial positive, partial negative. Let me go ahead and write this equals partial. Questions? So you can imagine if the oxygen wants electrons more, they're sharing in this bond, but the oxygen isn't sharing equally. It's keeping the electrons most of the time. I think your book has two dogs, a big dog and a little dog for a picture for this, okay? I always think about it like toddlers because I'm a parent, right? And so if you have a big toddler and a small toddler and they both want a toy, they're probably not going to share it equally. Big toddler is going to get the toy more of the time. Okay. So same sort of thing. We could do another one of these. Let's go ahead and do, let's do fluorine and nitrogen. Let's say I had a fluorine-nitrogen bond. Look at your periodic table. Which of those atoms is going to want the electrons more? Which one is more electronegative? A little louder, I think I heard it. Fluorine, yeah. And so I would draw it like my arrow like this. Okay? Or another way we might denote it is that we'd say fluorine has, really, I think the way we would denote it, so fluorine is more electronegative, so oxygen, or nitrogen is going to have a partial positive charge, and fluorine is going to have a partial negative charge. Okay, questions? All right, so we have this concept of polarity for atoms. And this is someplace where I'm going to give you a rule with a number, and we're going to stop just using trends necessarily because we end up in trouble with these trends sometimes. Okay, sometimes it's not as easy to see based on that. We're going to actually use an electronegativity table here. So this is a table of the electronegativities of the elements. Why is this column empty? Why did they give us electronegativities there? So I heard that multiple times. Great. Noble gases. They're noble gases. They don't want to share They don't want to share. They don't want to make covalent bonds. They're just really kind of not relevant to this discussion. Okay. They don't want electrons at all, but they don't want to give up electrons either. Okay, which is kind of part of what this concept is. So your book has if we want to think about polar bonds versus nonpolar bonds, it has a nice little kind of line here, really. And so what it talks about is, we're going to talk about the difference in electronegativity between atoms. All right, if we're looking at a difference, so we're going to subtract one from the other, and this is actually an absolute difference, okay, the way this is talking about it. So I could put absolute value lines around that. This would be 0.5. We could think about 0.5, and if you have less than 0.5 difference in electronegativity, we call those nonpolar bonds. Okay, and then if we have a difference of up to 2.0 is where they're drawing the line. 2.0, we're going to call those, these are polar bonds. And then here, 2.0 and greater, they become ionic bonds. In other words, the sharing is so bad that one atom takes the electron from the other and doesn't share. Does that make sense? So if we took, so just talking about that one, if I took, I'm going to do my Lewis, what is it called for atoms? My atom dot structures. Here's a place that's useful. Okay, if I had a chlorine come up with a hydrogen, if we look at the difference in the electronegativities here, the electronegativity for hydrogen is, come on. The electronegativity for hydrogen is 2.1. We'll see it up above, and then we'll look up the electronegativity for chlorine. All right, I see what was going on there. And chlorine, it's 3.0. Okay, I don't know if you can see that, but that's a 3.0 there. If you look up the notes later, you'll be able to see that. It's also, that figure is also in your book. Let me get rid of all these I's. Okay. So the electronegativity is equal to 3.0. We got another electron there. So 3.0 minus 2.1. Actually, this isn't going to do what I want. 3.0. It is 2.1, isn't it? I'm not going to prove my point. Yeah, I'm just going to have to come back to that, because I do know that chlorine does take that electron away, and fluorine does not. Yep. It's going to be more complicated than that. I'll come back to that one next time. All right, so let's talk about polar molecules. All right, so if we look, and let's think about, so for ionic, I'm not sure on that line. But for polar versus nonpolar, I'm sure. Okay, use this rule a lot. And so I want you, let's concentrate on that line right there. And so if we come down here and we look at the electronegativities of these atoms, what was carbon is probably 2.5. Yes, okay. So the electronegativity of carbon is 2.5. The electronegativity of oxygen is 3.0, right? All right, and so we do have a polar bond. So the 0.5 and above is going to be polar. It lands on 0.5. So we have a polar bond here for this molecule. Here we have the electronegativities are 2.1 and 3.0. All right. So the difference here is 0.9, right? All right. So the difference here is 0.9. Let's go ahead and write down the differences too. I'm going to type it. All right, so the difference in electronegativity equals, this one's going to be 0.5, okay? So this means we have polar bonds, okay? Over here, the difference in electronegativity equals 0.9, right? 3 minus 2.1, 0.9, so polar bonds. So polar bonds in both cases. But when we look at the molecules here, there's no net dipole here. In other words, if we think about the molecule as a whole, we've got them pulling in opposite directions. They're symmetric. That makes sense? So that is not, CO2 is not polar. Okay? Water is polar because we have a net dipole in some direction for the molecule. A way I like to think about this is I think about, can I draw a plane through the middle of this molecule and end up with one side is partially negative and one side is partially positive, right? So here, it doesn't matter what plane I draw through the center of that molecule, I'm still always going to have negatives on both sides of that plane, and the positives right on the plane. Here, I can draw this, and I'm not going to end up with any difference. It's symmetric, but I can draw, if I think about a center of mass for this molecule, I can draw this, and I have a negative side and a positive side. Does that make sense? In terms of polarity. And this polarity is going to be very important in terms of when we think about what kind of molecules dissolve and what other molecules. Okay, and you've observed this in life. We'll talk about some examples of that. So let's talk about let's just give some rules for what we need to have a polar molecule. So to have a polar molecule, we have to have the following. Okay, first thing, you have to have polar bonds. All right, and when we talk about having polar bonds, we have to have polar bonds, so what that means is you have to have an electronegativity difference between at least two of the atoms in your molecule that's greater than 0.5. Okay, 0.5 sticks for that set of rules up above. All right. And then those polar bonds must not be symmetric. The polarities from the bonds okay, so they can't cancel each other like what we see for this carbon dioxide. All right, so but my rule is going to be, we talk about symmetry, we talk about them canceling, but there needs to be a partial positive side and a partial negative side, at least partial. That makes sense? Have to have a partial side, at least partial positive and partial negative. I didn't say that there. I just said positive and negative, but I mean any chain charge. If you have a positive and a negative, full positive and full negative, that's polar as well. Questions? All right, so this is really important to the the qualities of molecules and the properties we see for molecules. So let's go ahead and let's scoot back up here. Let's look at sulfur. Okay, let's not look at sulfur. Let's look at, okay, let's look at ammonia is what we're going to do. So if we take ammonia, right, here's my Lewis dot structure for ammonia. All right, I've got 4 things around the center atom, so its electronic geometry is tetrahedral. Its molecular geometry, it only has 3 atoms attached to the center atom, so it's going to be trigonal pyramidal. Okay, essentially, this triangle of atoms is going to be pushed down by that pair of electrons sitting on top. This is trigonal pyramidal. Okay, and then if we go up and we look at our chart again here, 3.0 for nitrogen. All right, so the electronegativity of hydrogen is equal to 2.1. The electronegativity of nitrogen is equal to 3.0. So the difference is 3.0 minus 2.1 or 0.9. That's a polar bond. Okay, because the difference is greater than 0.5. Which one's more electronegative? Where's the, actually, let's not even ask that. Let's ask, where is the partial charge, where's the partial negative charge going to be in this molecule? Is it going to be on the hydrogens or is it going to be on the nitrogen? The nitrogen, right, thank you. So what I can do is I can draw these little arrows, right? Okay, so I'm drawing the arrows showing that's more negative in that direction, but so that alone in the way I've drawn it would make it look like it is polar, but you want to make sure that you have the 3-dimensional, you're thinking about the 3-dimensional shape. And remember, what we can do is we can represent things coming towards us out of a molecule with these little wedges, and we can use these dashes to imagine them going back. So imagine I've got my trigonal pyramid like that. It has arrows going like this for the polarity. And so you can see that the net polarity here, I'll do it in red over it, would be that, right? And so I have a partial negative charge up here on the nitrogen, and I'm going to have partial positive charges down here on my hydrogens. I have, if I think about doing this across the center of mass of the molecule, I end up with a positive side and a negative side. It is polar. Okay? Does that make sense? So ammonia is polar. Okay. All right, and so before we move on, you need to be able to do this, determine whether a molecule is polar or not. I just want to talk about the difference in these two molecules. Anybody ever worked with ammonia? Anything about ammonia? It smells really bad. It's toxic, but it's toxic in a way that it smells so bad it will drive you from the room before it kills you, which is good for toxic molecules. But this is polar. This readily dissolves in water. Okay? Carbon dioxide is nonpolar. Okay? It doesn't dissolve very well in water. What examples do you have of that from real life? Soda, yeah, soda, right? So soda has carbon dioxide bubbles in it. And what's going on there is they put the carbon dioxide bubbles into the water that is what's most of your soda. And then they put it under pressure to get it into the water. Okay? And then they close it off. And then when you open your bottle or your can, what happens? Bubbles start coming out right away, right? You see bubbles coming up. That's carbon dioxide coming out because the carbon dioxide is not very soluble. They had to put it under high pressure to push it into the solution. All right. Questions about polarity? All right, I will put up practice problems for those as part of your homework. We're going to move on, and we're going to talk about, we're working up to talking about molecular orbitals here. All right, so we're going to talk about molecular orbital theory. This is a basic introduction. So so far we've had some different theories, and this week in lab, you're going to talk about, I think you're going to do some molecular orbital theory, because I'm supposed to have taught you what bound order is, right? That comes from molecular orbital theory as much as anything else. But you're also going to remember we talked about valence. We'll talk about valence hybridization theory, okay, where we mix some orbitals that you also need for lab. But in terms of this class, I've talked to you in terms of all of chemistry. I've talked to you already about how we have models that we use to explain the world. And in terms of teaching you chemistry, we start with simple models and we work our way, simple molecules that kind of do the job we need at the time. And then we work up to more complex models as we go along. Okay, so Lewis dot structures, super useful. You will use, if you continue to be a chemist, you will continue to use Lewis dot structures, okay? Simple, easy, gets the job done a lot of the time. All right, so I haven't taught you something there that you're going to have to disregard later. I've used Lewis dot structure my whole life. And it's an amazing model. It's a simple model. It explains tons of stuff. I can get most of the shapes out of it, okay? Awesome. I marvel at it. I don't know if you guys do, but I marvel at how cool it is that something that simple actually explains the world well enough to be that useful. So a more complicated model though, so we have trouble describing using Lewis dot structures. Well, we do have an explanation for it, right? But in terms of where the orbitals are, we have a trouble explaining shapes like the tetrahedron, right? Why do we get a tetrahedron when that's coming from, when we think about our atomic orbitals, we've got one spherical orbital, and then we've got these orbitals that point in the 4 different Cartesian coordinates, right? The 4 coordinates of three-dimensional space, three coordinates of three-dimensional space. So we mix those together, and we've got this theory where we mix them, and we come up with those hybridized orbitals. We talked about those before. I don't want to spend more time on them now. You'll talk about them in lab this week, and if you take organic, you'll talk about them a whole lot. All right. In organic, that's a theory that gets used a lot. Okay. More complex model. All right. Explains things really pretty well for a lot of organic chemistry. All right. However, there's things it doesn't explain. And so we're going to go to one more complex molecule model that I'm going to introduce here today. And I want you to know about it because you may see it later. So in organic chemistry, you'll talk about molecular orbital theory and use it some. And then as you go further on in chemistry, molecular orbital theory does an even better job of explaining things. Okay, but it's much more complicated. There's lots of calculus and complicated math. And we're not going to do that complicated math today, but we're going to talk about some of the results and how to think about it. So let's think about electrons. Okay, remember that electrons can be a wave or a particle. Okay, and so really anything can be a wave and a particle. We talked about this briefly. That was that de Broglie equation. If you remember from the first test, we had the de Broglie equation. Everything has a wavelength. That wavelength really only becomes relevant when things become really tiny, like electrons. All right, nuclei can maybe sort of have it, but you don't get wave properties much higher than that. And so a wave, this is an example of a wave right here. If we think about a wave of light, it's like a wave in the ocean, but out before they crash out at sea, you might see a wave and it would go up and down and up and down and up and down like that, more even than what I've drawn. So when we think about a wave of an electron, we can imagine in one dimension, you can imagine it being around the nucleus, okay? So when we think about our atomic orbitals, our s orbital, that big sphere, is a standing wave. Okay, it's a standing wave. It's a three-dimensional wave around the nucleus. We're going to just do one dimension here for thinking about this. And so we can imagine that we have two atoms, right? We have two atoms here. They're going to come together, and they have these waves. And we can have those waves constructively interfere if they're in phase. So in other words, the place where these two come together, and note that this is more narrow than the sum of both of those, and it's more wide than both of them put together, which is how we're going to get that thing up there. But if I bring the two together, that these two will add together to make a deeper trough, right? Okay? So what they do is they constructively interfere with each other, and that makes it more stable. That makes the energy level that the electrons can be in. When these two things come together and then electrons occupy this orbital, that makes this orbital more stable. So let's go over here and we'll say constructive interference. And it's more stable. All right. But you could also have them come where they'll destructively interfere. So this one's going down, this one's going up, and so they're going to cancel to some extent. If I fully overlap these, I get a straight line, which is kind of how I wish they'd done this diagram, but that's not how they did it in your book. They had them, once again, this is wider, so we have overlap of maybe the first half of each of these. But they are destructively interfering. And so it's less stable. Does that sort of make sense? At a one-dimensional level here. All right, so these waves could come, depending on how that's going, they can then constructively or destructively interfere to become more or less stable. In terms of the orbital that the end, these are orbitals. This is where the energy, this is where the electrons live, essentially. All right. So just like, so we're going to do this, but with three-dimensional orbitals. We're going to think about this. And so if we look up here, just like in this example, we had 1, 2, 3, 4 atomic orbitals we were combining. When we put 4 atomic orbitals in, we need to get 4 orbitals out. Orbitals still only take 2 electrons each, right? Just that we're not going to really ever have a different rule than that. So we have 2 electrons each here. So here they're all spread out to be unpaired. If we had more electrons to put in, then we'd have to start pairing them, and we could put 8 in there total. That make sense? Okay, remember that? So, but the important point here is, however many atomic orbitals we put in, we're going to have to get that many. In this case, these are valence orbitals, but we're going to need to do for molecular orbitals, same thing. Okay, same number in, number out. Okay. So here we can think about doing this with the 1s orbitals. Okay, so this is a molecular orbital formed by the combination of the 1s orbitals from 2 different atoms. All right, it's 1s orbitals touching the out. This is atoms with their orbitals interacting, right? So it's got to be the outside orbitals. Which atom will have 1s orbitals touching the outside world? Which atoms? Hydrogen, right? Hydrogen and helium, right? Only two, okay? And so these things can interact with each other. So we're going to look at hydrogen and helium for this. So these can interact with each other. Here we have constructive interference, okay? So the waves of those electrons are going, if you do think about it in one dimension, the waves are coming down together or coming up together, whichever way. And if we have constructive interference, we end up with a bonding orbital. So we get this great overlap, okay? And if we end up with destructive interference, so one of these orbitals has a different phase, and in one dimension our phase is up, versus a different phase, one would be going up and one would be coming down, and they cancel when you add them together. Then we're going to end up with this space between the atoms where there can't be any electrons, because those wave functions cancel. And I'm saying wave function, you could just think waves. All right, and you can see the energy along the side right here. All right, so you got the energy. This is higher energy than this. And we call this bonding and this anti-bonding. This is stable. This helps hold atoms together. This is anti-bonding. This is unstable. It does not help hold atoms together. And so I think I've got, the next picture is this, yes. This is what we want to look at. So if this is for hydrogen, this is what we get. We look at one of these, so what we do is we're going to do, I'm going to redraw what's right here, but the way I think about it is I've got a 1s orbital for a hydrogen atom. Okay, I'm just redrawing this, but I just want to show you how, if you had to draw one of these, and you're not going to have to draw one of these, but you are going to have to fill in electrons, okay, and then analyze it. And I have a 1s over here. I can bring these guys together, these two 1s's. I've got bring two atomic orbitals together, two atomic orbitals. I need to get two molecular orbitals out of it. If I bring those two together, I get a bonding orbital that's more stable than the original hydrogen atoms. And I get an anti-bonding orbital that is less stable. Okay? And so this, we call this a sigma bond. You don't need to worry about that so much. I really want you to get a feel for more, bring two of them together, more stable, less stable, okay? And then we would fill in our electrons. How many valence electrons does hydrogen have? Periodic table. 1. So I've got one electron over here, I've got one electron over here, and then I fill them in. Electrons go in the most stable orbitals first. These are molecular orbitals. Okay, they're shared across the molecule. And so I'm going to go 1, 2, and then I don't put any over here. So all my electrons are in bonding orbitals. That's what holds hydrogen together as H2. Okay, and this is, we have one pair of electrons in a bonding orbital, right, in a more stable orbital. Okay, then, and when I say more stable, I mean more stable than the original hydrogen atoms orbitals, the atomic orbitals. 2 electrons makes how many bonds? 1, right? Covalent bond is 2 electrons. So this has a bond order of 1. Okay, and that's 2 electrons makes 1 bond. Okay, but only if they're more stable than the atomic orbitals here. Let's do helium. Okay. I'm going to just talk through this one rather than redraw it. But we will have an example where we can do some of this stuff. So helium, H2. Do you think H2 exists? Just before we even talk through this. No, is it just because I said it that way? Why doesn't H2 exist? Because it's noble gas, it doesn't want to react, it doesn't want to hang out with anybody. Even other people like it's even not people, but even other atoms like itself, right? Okay, it doesn't want to make any bonds with anybody, even other heliums. But molecular orbital theory tells us why this is the case. So if we look at this, we have 2 electrons for each heliums, right? We get that off the periodic table. To bring molecular orbitals together, we have 2 atomic orbitals here. We make 1 bonding and 1 anti-bonding, where the bonding is more stable and the anti-bonding is less stable than the individual atoms. If we then put these 4 electrons in, 1, 2, 3, 4, we end up with 1 bonding orbital and 1 anti-bonding orbital. They essentially cancel, and there's no reason for those heliums to come together. Does that make sense? Why we see that? This is bond. So what we have here is, this is going to have a bond order of 0. So no bonds. Okay? And so the way you could think about this, we could do bond order as BO. And then if we do bond order, if we can take number bonding, and you can have fractional ones, minus number anti-bonding. Okay, and so for what I've got right here, I've got 1 bonding for that lower orbital minus 1 anti-bonding equals 0. Questions on how we do that? All right, so if I was to give you these pictures, and I will have you fill them out. I won't have you make the orbitals. But if I was to give you these orbitals here, show you what the orbitals are, you need to figure out how many electrons you have and then fill them in. Okay, you're going to fill them in over here, and you're going to fill them in the middle. So well, I'll make up some practice problems in a bit. Okay. So we can do these. So far we've done these bonding orbitals just using the 1s orbital, right? But you can do this with the p orbitals as well, right? We have p orbitals that point at each other, right? You've got 2 atoms that snuggle up to each other. Remember, I've got a p orbital that points this way, I've got a p orbital that does this, and I've got a p orbital that does this, right? I've got one on each of the coordinates of the 3 dimensions. And so when I have 2 of them pointing at each other, it's like this. And what you end up with is you can end up with a bonding and an anti-bonding orbital. Okay, I'm just going to go over the pictures pretty quickly here. This is spherically symmetric, so it gets called a sigma as well. We gave that a sigma before, but this is a sigma p as opposed to a sigma s. But then I have 2 other p orbitals that are not pointed at each other. And these end up being important. We talk about double bonds. This is where we get our double and triple bonds from. Okay, but you can see if I bring these 2 things, if these are, I'm going to bring them up next to each other, but they're pointed up and down. They come up like that, and then we can end up with our bonding orbital, and we can end up with our anti-bonding orbital. That's how that works. And you see here the phases of these are different, at least in terms of the colors. You see how we get those? But it's 1 p, another p come together to make a lower p, a bonding p, and a non-bonding p. We're going to go to more complex atoms and hydrogen here. That's where we're headed. Before we do that, I remembered that I had a movie for this. I have something I want to show you. So I want to show you a place this is useful. Okay, what molecular orbital explains, the theory explains that that our other theories do not. Where do I go for my bookmarks? Is it over here? Bookmarks. There we go. Maybe the bottom of this. That's not it. Is there like a more bookmarks? Other bookmarks. There we go. This is the one I want. Oh, this is going to take 3 minutes too. After we see our, what is this? Liberty Mutual. Okay. I'm going to actually try and speed this up, especially since I don't seem to have the sound hooked up. No, thank you. I've thought about it. Yeah, my sound isn't into the system, so I'm going to talk about what Daniel's talking about here. So what he's got is he's going to make some liquid oxygen here, which is fun. They don't let all they let me do is like baking soda volcanoes around here for demos anymore. But I used to be able to make liquid oxygen, and usually it was to blow up things. But so what we've got here is he's got a big magnet. This is a big magnet, okay? What he's got here is he's got a dewar, and he's going to run oxygen through liquid nitrogen. And if you run oxygen gas through liquid nitrogen, it actually condenses to make liquid oxygen, okay? And what we'll see here as he gets it is it's this beautiful light blue color, okay? Which you should also characterize if you ever see something like that, and it's this beautiful light blue color. That is danger, okay? Stuff is pretty dangerous, okay? What he's doing is okay. It's not dangerous on its own, but essentially you could take a charcoal, I don't know if anybody seen this video, you take a charcoal briquette, you soak it in liquid oxygen, it goes off like a stick of dynamite because it's got all the oxygen it needs right there. All right, so that's where you need to worry about it. If it is purple, that's ozone. Okay, I think you have to do special things to get ozone. Ozone will go off on its own. So I have my brother-in-law used to work on this at Virginia Tech. See the beautiful blue color there? It's not very, but okay. But ozone will go off on its own. You should run if you see purple. Okay. All right, so we're going to have to look. So now he's pouring liquid nitrogen on the magnet. Okay? You see any liquid nitrogen sticking to that magnet? I don't see it sticking. There, right there. All right, no liquid nitrogen sticking to the magnet. I'm glad he has his safety glasses on. Now this is liquid oxygen. Look at this. And he's going to pour a little more. It's even better. That's pretty good. But yeah, he's going to pour some more. Watch him pour some more here. Actually, you know what's going on right now? It's evaporating off. You got to pour some more on just to make sure the magnet's super cold so it doesn't evaporate away. Look at that. So oxygen sticks to a magnet and nitrogen doesn't. How do we explain that? Do our Lewis dot structures tell us anything about that? They don't. I'll answer it for you. I want to make sure I get this done. I don't want to close that though, because I might lose. All right. So let's go back and let's real quick just look at Lewis dot structures for oxygen. What do you guys know about compounds sticking to magnets from lab? I don't know where those O's are going. Wow. Hold on. That's where they're all going. All right, so oxygen. Lewis dot structure looks like that. Nitrogen. Lewis dot structure looks like that. All right, I only have 5 minutes here, so I'm not going to let you think about it too long. But what do you know? Do you remember from lab? It's whether you have paired electrons or not, right? If you have unpaired electrons, something sticks to a magnet or is attracted to a magnet, right? If you have paired electrons, it's diamagnetic, it's slightly repelled, okay? See any unpaired electrons in oxygen? In Lewis dot structures? No. Okay, there are no unpaired electrons up there. They're all in bonds paired, or they're all in lone pairs paired, okay? So how can we use Lewis dot structures to explain this? All right, well, what we're going to do here is this is a little diagram from your book that talks about how you draw the orbitals, but I'm going to draw the orbitals for you. I'm trying to remember if the next one is unfilled. Oh, that's more important. Okay, it's not. So let's go ahead and look at this for oxygen. All right, so these are our little diagrams from our book that tell us which way we're supposed to draw these depending on where we are in the periodic table, which you don't need to worry about because I will draw them for you, but you will need to fill them in. Let's go ahead and do this for oxygen. So oxygen has, in the outer shell, we have a 2s orbital, right? And we have another 2s orbital. So let's say I've got an oxygen coming up to an oxygen, right? They're going to bond together. We know they're going to bond together because they do, but let's explain why. So we have a lower energy orbital here, which is a sigma bonding, and a higher energy orbital up here, which is a sigma anti-bonding, which we do with a little asterisk. And then I have 3 2p orbitals that are all the same energy, and they can break up into, there's a sigma p that's bonding, okay? And then there are 2 pi that when they're on the sides, remember when they were on the side there? Those, we call those pi bonds. They'll be more important in organic. Those are also bonding. Pi, pi, and then our sigma. Note that my sigma here, if it's really stable, it's really unstable, right? Okay. So what I'm doing is I'm just doing this thing over on the left here. Oxygen, how many valence electrons do we have? So these are 2p's. 6, okay? So 1, 2, 3, 4, 5, 6, okay? Unpaired there, but we're making a molecular orbital. 1, 2, 3, 4, 5, 6, okay? Now let's explain oxygen structure using this. How many total electrons do I have? 12, right? 6 plus 6, okay? Note also that I had, what, 8 orbitals, and I got 8 orbitals, 8 atomic orbitals, and I got 8 molecular orbitals. All right, need you to pay attention here. This is the payoff, okay? So 12 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Note how I unpair them if I can at the same energy. Oxygen has 2 unpaired electrons. So O2 has 2 unpaired electrons. That's why it sticks to a magnet. If we did this for nitrogen, what we would get is we would get no unpaired electrons. Okay? So I might have you practice doing that if I do for a problem. One more comment I want to make here. Let's do bond order. Okay? How many bonding orbitals do I fill? 1, 2, 3, 4, right? 4 bond order equals 4 bonding minus how many anti-bonding? I've got 1 anti-bonding, right? And then 2 anti-bonding, right? Because 2 electrons across the 2, does that make sense? Right? 2 that, so minus 2 equals a bond order of 2. That's the same number of bonds that we've seen from our Lewis dot structure, right? Oxygen has 2 bonds. If you do nitrogen, you will find that it has no unpaired electrons and it has a bond order of 3. All right. You guys have fun. Enjoy your lab. See you on Wednesday. And if anybody wants to talk to me between 1 and 3 today, come let me know.